This video deals with configurations, specifically configurations that can occur inside of a Cartesian plane over some field. Okay, so things to remember when we're dealing with configurations. The first thing is, how do you spot that you're actually working with a configuration? So, spotting a configuration. Don't overthink it. A configuration is simply some subset of points and lines from your Cartesian plane. So in terms of what you see, you have some or a set of points and lines. So that's what you're visibly seeing, and that's in some Cartesian plane. And remember, a Cartesian plane over any field is an incidence geometry, so you're literally looking at some subset of points or line in some incidence geometry. Okay. Now, dealing with configurations, which is a whole nother ballgame. First thing that you want to do, label your points. Sometimes it'll be all of the points that you need to worry about. Sometimes it's only some of the points that you need to worry about. And from context, you should be able to tell which it is. When in doubt, label all your points. Okay. Second thing you want to do is we're going to apply our proposition 14.2, which says there's a linear change of variables. So, use the notion that you can always do a linear change of variables. And this is simply applying proposition 14.2. Okay. So what do? You identify one of the lines of your configuration to be your new x-axis. You identify one of the lines, can't be the same line, to be your new y-axis. And here's the thing that you have to have. The two new lines must intersect each other. Why? Because the x and the y-axis intersect at the origin. Then you identify the origin. This will be determined as soon as you get your x and your y-axis, because this is the intersection of your x and y-axis, or plural axes. Okay. You then go ahead and pick your unit points. And remember, unit points are simply the points that are going to be tagged as 1, 0, and 0, 1. And the only specification on them is they have to be on the respective axes, and they can't be the origin. Why? Because 1 and 0 are not allowed to be the same object. Okay. And typically when you're in these configurations, you have at least 1 or 2 points where you say, hey, you know what, I don't know what point this is. I'm going to put in a variable as a placeholder. So here, often or typically, you have at least 1 point that looks similar to this, c equals something, comma 0. So this would be where you have an arbitrary point on the x-axis. Maybe you know everybody on the x-axis and you have this point instead on the y-axis. Okay. Key thing is this point where you've got this unknown or this variable, this placeholder right here. That guy is pretty much key for most configurations, and they should only be on the axes. They shouldn't be anywhere else. Okay. In terms of where you define them. Now, other points not on the axes, using now this variable a or this stand-in letter a, yes, sure, that's no worries. All right, so third thing we do, so next we find all the points in your configuration, or really singular configuration. Pretend there's no s there in your configuration in terms of your number 1, and whatever variable you had to throw in there. So like for example, right here, we said, hey, we don't know what point C is, wherever C was, but we're going to throw in this placeholder variable of A. Okay, so you find all of your points in the configuration in terms of either one or those variables. And when I say in terms of one, that means all field operations on one. So that means one added together in as many times as you want. So that gives you all integers. One multiplied by anything you want. Again, you can get your integers. One multiplied by anything you want also deals with one multiplied by reciprocals. So that also means you get any fractions you want. So when you say something here of the 1, this means you get all numbers that would roughly speaking have a one-to-one relationship with all of your objects from the rationals, or you essentially get any fraction you want. Notice what you don't get for free. You don't get for free any irrationals, so no fractions, no pi's, no e's, no imaginary numbers like I, none of those other, non-rational numbers do you get. Okay. Now, what else do you want to do at this stage in the game? You're not going to be able to find all of the points in your configurations in terms of one of your variables or at all unless you start figuring out what some of the equations of your lines are. So we also need to go ahead and find or determine all equations of your lines and the configuration. And specifically here, again, you want them in terms of something that looks like a fraction and whatever your variable is if you have one. And note when we say this in terms of, we are specifically talking about if it's a y equals mx plus b format, both the slope and the y-intercept need to have these type of numbers. So something that looks like a rational or some expression of your variable. Now, let's actually write that out a little more specifically. So here's the y equals mx plus b. You could also just have a constant, and you could also have a vertical line. So here what this tells you is the m, the b, the c, and the d. All of those guys need to be written in terms of these variables. So in terms of, fractions and the variables. Okay. Now, last thing that you do with the configuration is figure out what in the world you were supposed to do. So answer whatever question was asked. Answer question ask. Okay. In this course, most of the things that we're going to be looking at is answering the question, when does this configuration exist? What type of field do you have to have? What elements do you have to have in your field in order for your configuration to exist? But you can have lots of other things that you do deal with as well. Okay, so remember that's the strategy in terms of what we're going to deal with when we deal with configurations. So I'm only planning on going over one example in this video, and that example is this guy. So this is actually from your textbook. This is from section 14, and it says, hey, you're in some sort of Cartesian plane over some field F. So this is exactly the same as in terms of symbols, looking at this guy, capital Pi, and the subscript F. Now, we don't know what the field F is, but we do know that the characteristic of the field is 0. So this means the smallest field that we could have is rationals, or somebody isomorphic to rationals. So we'll have guys that look like rationals, or maybe you throw in some square roots. Maybe you get all the way up to real numbers for your field. Okay. What we want to know is about this configuration. So there's a configuration, and it's given right here in the diagram, where all the lines that appear parallel are parallel, and I went ahead and listed them all out. So DE is parallel to BC, DF is parallel to AC, EF is parallel to AB, GH parallel to BC, and BH, where's BH? BH is parallel to GE. Okay. And the claim here is we're only going to get this configuration when or if the square root of 2 is actually inside of our field. In other words, this is telling you, hey, the smallest field that contains this configuration in its Cartesian plane is going to be Q adjoins square root 2. So I'm going to write this up at the top. So note, this would mean that the smallest field where the configuration given is in its Cartesian plane is Q adjoins square root 2. And I can say that without going anywhere further because this is claiming that square root 2 is the condition we need in the field. Okay? And this here would be the smallest field with characteristic 0 that actually includes a square root 2. Now, are there bigger ones? Sure. Real numbers would work too. Q would join both the square root of 2 and the square root of 3 would work as well. Okay? Now, if we actually want to show that this is true, so what we want to do is we want to look through this configuration. We want to say, all right, do we actually believe that square root 2 is the thing that's needed? Okay? What do we need to do? Well, the first thing is we need to approach this like we would any other configuration. So the very first thing that we would do, so step 1, we need to label all of our key things. So this is where we're going to, well, normally we would at the very beginning label all of our points. All of our points are already labeled. So skip that for a first step. Once all of your points are labeled that we're going to care about, and notice here, we did not deal with any of these points on the inside right here, simply because they were not endpoints of one of our line segments, so they're not going to actually matter here. So next thing that we want to do is we need to find all of our key pieces of information. We're going to identify our x-axis, our y-axis, our origin, our unit points, and then start labeling everybody. Alright, so in this case, our x-axis, I always like to take some of the bigger lines possible. And for the x-axis, I always look at the biggest line possible that's as far down in the picture as possible. So here, our lowest line segment would be BC. So I'm going to go ahead and let BC be our x-axis. Could you pick another line? Yes. Really the only criteria for picking your x and your y axes are the two lines actually have to intersect each other, but I'm going to try to make our lives a little easier. So for the y-axis, it needs to be some line that intersects BC. So we have 1, 2, 3, 4, 5 candidates. We're only going to pick one. I'm always pick the line that's to the leftmost of everything possible. So here I'm going to go ahead and pick AB to be the y-axis. Again, these are not the only possibilities. Now, once you've picked A, B, and BC to be your y and x axes, there's exactly one point that's allowed to be the origin, and that's their intersection point B. Okay. Next step, we'll go ahead and we will pick our 2 unit points. Now, for the unit point 1, 0, we have 2 options. You can either pick F or you can pick C. It doesn't matter which one you pick. So I'm going to go ahead and pick F to be our unit point. Now, for the other unit point, the unit point that's on the y-axis, our options are G, D, and A. Again, it doesn't matter which one of these you pick. Personal preference. I'm going to go ahead and in this case pick point D. Alright, so I went ahead and labeled these points on the actual configuration as well. So unit point F, unit point D, and since we know that BFC is the x-axis, I labeled all of the y-coordinates 0 on all of the points. And since we know A to B is the y-axis, I went ahead and labeled all the x-coordinates of these points with a 0. Okay. Now, next thing that we want to do is we want to look at some things that we know for sure. And the question, of course, is there anything that we know for sure? And the answer is yes. This is where we need to look back at the lines that are parallel to each other. So lines, let's label this as lines. Step 2. Okay. So we know that some of these lines are parallel to each other, so maybe you decide you want to look at BC. Well, we know BC is the x-axis, so it's right down here. And we're also told up in the given information that BC is parallel to DE and to GH. So DE and GH. Now, I don't know what GH, I don't know what point G is right yet, but I do know point D is 1. So point D being 1, and this guy being parallel to the x-axis tells you a couple things. We know that BC is the line y equals 0. We know that DE has to be the same form, y equals a constant. Well, point D tells us the constant, that's a 1. That, of course, gives you your point E. Has to have a y value of 1. Okay. Now, GH. For point GH, well, this is the stage where you can actually pick a little dummy letter right here. We can go ahead and say, hey, let's go ahead and pick that to be letter A. Okay. In that case, so I'll go ahead and add that in somewhere. Let's go ahead and add that in right up here. So let G be 0A, where we want or need A to be inside of whatever field we have. Technically, I probably should have inserted it right down here, but I forgot to leave myself room. Okay. So this then would tell us that our line segment GH has to be a line y equals some constant. Well, it would be y equals that constant A, which would tell you that H, the point, has to equal, well, I don't know what x coordinate, but the y coordinate would have to be A because you're on that constant line. Okay. Now, we can do the same sort of things with the lines that are parallel to the y-axis. So our y-axis is AB. And we have been told that the only line that's parallel to AB was EF. Now, AB, y-axis, means its equation is x equals 0. Nothing wrong with that, and in fact, we already dealt with that when we put in the x-coordinates equaling 0 on all of these guys right here. Okay. So, when we then look at the line EF, oh, I would love to be somewhere in the middle between those two guys. Let's try this one. All right. So if we then look at the line EF, has to be parallel to AB, has to be parallel to your y-axis, so it's going to be of the form x equals some constant. Well, I don't know what E is, but I do know what F is. And notice here, F is 1, 0, so what's the constant going to be? It's going to be x equals 1. And as soon as you have x equals 1, notice this is where we can go ahead and get our point E. Specifically, we found both from the line DE, the y-coordinate had to be 1, and from the line EF, the x-coordinate also had to be 1. Okay. So that gets us our point E. Now, in terms of what we're doing next, notice what we've got. We still have to find our point A way up here. We still have to find our point H, and we still have to find our point C. So let's look at some of these other guys. Now, we were also told, let's see, DE, BC, we got that one, DF, and AC. Ooh, we haven't used that one yet, but that one might be a good next one to look at. So, if we're still looking at lines, these guys being our vertical and horizontal lines, if we look next at DF, parallel to AC, quick check. Anybody else parallel to AC? Nope, so just these two guys. AC, we don't have enough points to give the equation of this line, but DF we do. So if we look at DF, wow, that's not a D or an F. Here, our slope is change in y over change in x. So if we look at our 2 points, D and F, the change in y coordinate is 1 minus 0 when I did D first. Still doing D first, x coordinates are 0 and 1, and this means we have a slope of -1. Now, the nice thing is, DF, we know immediately what our y-intercept is. It's point D. So this is totally the line y equals -x plus 1. Okay. Now, this doesn't pick us up any extra points right here, but it does give us the equation. It will give us the equation of the line A through C. So if we have A through C, the line, we know the slope is -1 because it's parallel to DF, and we also have the point E that we already found on that line. So going ahead and putting those two pieces of information together, we have the equation of a line is y minus 1 equals -1 times x minus 1, and we'll just go ahead and simplify that. So this is y equals, well, we have -x plus 1. If we add 1 to both sides, we'll get y equals -x plus 2. At this stage, we can go and solve for all of these points. Okay? So for the first point, we're going to plug 0 in for x, which gives us simply a +2. The last one down here, we'll plug 0 in for y. 0 in for y says -x plus 2 equals 0. Move the x to the other side, and we'll get x equals 2. Okay. Now to find the h, that's the only one that takes a little bit of work, so let's go ahead and I'll actually put in that work. So finding point h. H was y equals a, so we'll have a equals -x plus 2, and putting that all together, we'll move x to the other side, subtract a from both sides, you'll have 2 minus a. Okay. So this tells you that h, the point, equals 2 minus a, and then y also equals a. And that sort of makes sense if you look at the picture. This line, as you follow from C back to A, is getting closer to the y-axis. Okay. At this point, what do we have? We've got equations for all of our points. Okay. So equations for all the points. We should also have equations for most of the lines. Let's double check here. We've got the equation for AC. We've got the equation for DF. Check. We've also got the equation for, what else? We've got these guys. We've got those guys. GE and BH. I don't think we've done those guys yet. Okay. So let's pick up GE and BH. Now, if we focus in on GE, we have point G and we have point E. Scroll up so you can see the picture. Notice E and G. So let's go ahead and grab this slope right here. Match my notation. So the slope is change in y over change in x. So if you subtract the y coordinates here, I'm going to start with G first. Y coordinate of G is A, y coordinate of E is 1. Actually, both the coordinates of E are 1, so I went ahead and put the 1 down there. And the x coordinate of G is 0. Put this all together, and we have negative A minus 1, so I'm just going to flip the signs. And this would be 1 minus A. Okay. Now, g here at 0a is also the y-intercept of this line, so we can go ahead and put this all together. So this line would be slope is 1 minus a, x plus a, the y-intercept. Now, when we look at BH, the slope still has to be 1 minus a, and BH, B is the origin, so this tells you that this line is y equals 1 minus a times x. Now, here's the interesting part. We found the slope of BH just by copying the same slope that we had from the previous guy. But BH, we actually know both of its coordinates. We know the origin, that was one of our initial points, and we have the found point h. So let's see if we can't find the slope of BH a different way. Okay? So I'll mark what we did here. This here is simply because GE and BH are parallel. But suppose we used points B, which is 0, 0, and H was 2 minus a comma a to find our slope. Well, then our slope, it's still change in y over change in x, but the formula will be a little different. So subtract the y, so I'm going to have a minus 0, and on the bottom here for the x's, I have 2 minus a minus 0. So this is a over 2 minus a. So that's the second way to find this slope. But notice, when you plug this in, we get the equation for the line is y equals a over 2 minus a times x. But those two guys are supposed to be the same. I'm going to put a question mark there. Not that we really question it, but that it should be the same. So what do we want to do? We'd like to solve for a. We now have two different expressions that involve a, and they're supposed to be equal. So what do? We'll set them equal to each other. So we set the two formulas for m equal to each other. So this will be the original one, which was 1 minus a, and now the new one, which is a over 2 minus a. And now we just solve for a. So we'll cross multiply, or we'll multiply both sides by 2 minus a. So this will be 1 minus a times 2 minus a. And when we multiply the fraction by 2 minus a, you just get a. Now we'll FOIL this out, or we'll multiply out. And when we multiply out, we'll have 2. We'll also have a squared, and then the middle terms are where we have to multiply those guys together, so we'll have negative 2a and negative a, so that's negative 3a. Now I'm going to clean this up to make it a little nicer looking, so I'll put a squared first. I'll go ahead and move this a to the other side, so that should be negative 4a, and put the 2 on the end. Now at this point, we're ready to go ahead and plug this into a quadratic equation. And when we plug this into the quadratic equation says take your coefficient on your a term and take the negative of it. So negative 4. Then we're going to have a square root. You take the coefficient on the a term and square it, minus 4 times the coefficient on the a squared term, multiplied all by your constant. All over 2 times the coefficient on your a squared term. And of course that's a mess, so we'll clean that up. So this is 4 plus or minus stuff under the radical, all divided by 2. So let's actually deal with stuff under the radical. This here is going to be 16. This is going to be 8, so 16 minus 8 deals with square root of 8. So this is the same as 4 plus or minus 2 root 2. I went ahead and pulled a factor of 4 out of the root. And remember, you have to take the square root of 4 when you pull it out, so you get that 2. So this is exactly the same as 2 plus or minus the square root of 2. Now, often you don't get that fraction to simplify, but what you always want to do is you want to simplify the radical as far as possible. Why? Because what do we need? We need A to be inside of our field always has all of the information coming from Q automatically, or at least isomorphic to Q automatically. So we've got this 2 out front, no worries. The only thing that you don't naturally have in the field of rationals is the square root 2. Now, quick check. There are 2 possibilities here, but A really is only one of them. So we look back up at our picture, and we look where A was. A is supposed to live between 0 and 1. So scrolling all the way down here. So if you add square root 2, it's going to be something bigger than 2, so that's not the one you want. So here A is really 2 minus root 2 in this case. Okay. Now, conclusion. In order for A to be in the field, we must have square root 2 in our field in order to get A in the field. And note, we must have A in the field to have this configuration in the field's Cartesian plane. Okay. And something we talked about at the very beginning, the smallest such field with this configuration, or with this configuration in its Cartesian plane, is isomorphic to Q adjoins square root 2, which is given by the set. Oh, it's normally used with A's and B's, so I'll just go for it. Where you have some fraction plus some fraction times square root 2. And just as a second heads up, this is a field that is properly bigger than the set of rationals, or the field of rationals, but it is not yet as big as all real numbers. Why? Because in this thing, you don't have anything like square root 2. I lie, you have square root 2. You don't have anything like a square root of 3. Or e or pi or anything like that either.